Well, hi everyone. In this video, I'd like to talk about linear systems of differential equations. This video is really intended to show us the power of linear algebra as it pertains to solving multiple differential equations all at the same time. It's a culmination of a lot of blood, sweat, and tears to prepare ourselves for studying this type of situation based on a lot of linear algebra background. And we're going to see a lot of linear algebra throughout this topic for sure. The fact of the matter is that most mathematical problems involve more than one unknown function. There's usually not just one unknown. There's usually many unknowns that are related to one another, generally by a system of differential equations. Just to give you one real-world example, you might remember a situation where we could take a tank that has chemicals dissolved in a solution here. And, we have some amount of chemical, I'll call it A of T, in this tank, and it changes as a function of time because the tank is leaking a little bit, and so there's an outflow rate. Maybe the rate of the outflow from this tank is R2, and there's some concentration of chemical also leaving that tank. Let's say it's C2, and meanwhile, we might be pouring chemicals in with a concentration of C1 and at a rate of R1 as well. So this is a single mixing problem that involves one tank with one amount of chemical in it as a function of time. And we can set this problem up as a differential equation for the unknown function A of t. But now I want to imagine that we had actually not just this one tank, but what if we actually had a second tank? What if we had a second tank with, let's say, a different amount of that same chemical, let's say B of t, as a function of time? And let's imagine that there's chemicals pouring in to this tank as well at maybe a rate of R1 prime and a concentration of C1 prime. So these are just different numbers, right, than what we might have had on the first tank. And then we could also expect that perhaps the chemical is leaking out of the second tank as well at a rate of, let's say, R2 prime and at a concentration of C2 prime. So we could have a completely different problem here with a different tank with different numerical values, and we could solve that as a differential equation as well. But where it gets interesting, where we see the more than one unknown function being related to each other, is what if these two tanks are actually connected to each other by a piping system that is pushing the chemicals either to the left or to the right from one tank to the other, right? Or maybe it's moving in both directions. Now, the A of t will actually depend on the B of t, and the B of t will depend on the A of t. All of a sudden, this is not just one differential equation with one unknown function that we need to think about. No, this is actually a system, a linear system that would involve more than one unknown, in this case, A of t and B of t. And there's a system of differential equations that's going to relate those unknowns to each other. This is exactly what I'm talking about. Most mathematical problems will involve more than one unknown function. Okay, so with a little bit of motivation here, I hope this is motivating. There's, of course, many other examples that we could give as well from any number of other fields, from physics to chemistry to biology, you name it. You'll be able to come up with nice examples like this. But with this as just a brief motivation, I, of course, am going to focus more on the mathematical aspects of this. And to do so, I want to begin by just writing down what is a system of differential equations, a linear system of differential equations. I'm going to write it down once right here. It's kind of tedious to do it I'll call it a definition. We're only going to write it down in full generality one time, and then we'll start to actually do some specific cases. So a linear system of differential equations, which is what the title of this talk is all about anyway, is a system of the form. And now here's where we're going to have to do a little bit of writing to get the whole thing expressed, but I'm going to try and do it. The first unknown function might be x1 of t, so the derivative of x1, so that's x1 prime of t, could be thought of as maybe a11 of t times x1 of t plus a12 of t times x2 of t, and I'm going to go dot, dot, dot all the way up to, potentially there's many unknowns. Let's assume there are n unknown functions here. So the last term would be a1n of t times xn of t. And then to that, we're also going to add another function here, which could be thought of as a non-homogeneous contribution to the problem. This is b1 of t, right? So what I've written down here, guys, is just the first equation. It's the first differential equation in my entire system that I'm working on here. The second one might be x2 prime of t, the derivative of x2 of t. And this might look like a21 of t times x1 of t plus a22 of t times x2 of t, and dot, 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 we keep going, a2n of t, xn of t, and then plus b2 of t, right? Okay, and so we're going to keep going like that. And eventually we'll get to the last of the unknown functions, which would be xn. And I'm going to write the derivative of xn as a n1 of t times x1 of t plus a n2 of t times x2 of t, and we add dot, dot, dots to that, and we eventually get to the last one over here, a nn of t times xn of t plus bn of t. Okay, if you need to pause the video for a second to write all of that down with all of the subscripts and the notation, that is totally understandable, totally reasonable to do that. This is how it looks, and it's kind of uninspiring to see all of that sort of abstract notation up here. But, you know, the big picture of this is just that we have n unknown functions, and we have equations for all of their derivatives. But all of their derivatives are involving all of the functions. So they are interrelated to each other. That's what makes this a linear system of differential equations. We have n unknowns, and we have a whole bunch of other scalars. These are scalar functions of t that we would have to be given, right, on a particular problem. By the way, I like to think of t as time. Okay, so unlike other chapters of the book where the unknown function was like y of x, here you're going to be seeing x of t as a more common notation. The x is sort of representing the unknown function, and it's a function of t. All right, now the first thing I'm going to do here is I'm going to rewrite this in a much nicer way so that I don't have to keep writing this out all of the time. First of all, I'm going to suppress the t everywhere in here. Every single thing you see in all of these equations is a function of t. So that's just going to be kind of understood. So we're just going to understand that there is really a function of t here. And I'm going to kind of create a vector for these derivatives of these unknown functions here. And I'm just going to suppress the t. So x1 prime, x2 prime, and so on. But the reason I want to do that is you might notice on the right-hand side that we actually have a good old familiar dot product of the aij's and the x's going on here. And so I can actually express this, as we so often do, using a matrix multiplication. So the unknown functions, which are x1, x2, and dot, dot, dot down to xn. Those are going to occupy this column here on the right. And we're going to be dotting all of those x's with these a's, the coefficients, right? So we have, a11, a12, and dot, dot, dot. Again, everything is really functions of t here, but we're not going to write down the t every time. So the first row is a11, a12, all the way over to a1n. And then on the second row, we would have a21, a22, and dot, 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 all the way over to a2n. And we keep going like this down the matrix. And eventually we get to the bottom row, which would line up with the bottom equation, which is a n1, a n2, and dot, 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 up to a n n. And if you've been paying close attention, you might realize that this cannot be the final expression that I'm looking for, because in my original linear system that I wrote down, we have all of these b's over here on the far right of everything. So I need to add those over here to the right, b1, b2, and dot, 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 all the way to bn. Something like that would be the way we would write this. Okay, so now I've kind of re-expressed my system in a little bit more compact notation. I've suppressed the t's. I've taken advantage of matrix and vector notation to express this linear system as such. And of course, I'm going to abbreviate this even a little bit further. You will not be surprised at that. I'm going to abbreviate this even a little bit further by just using vector and matrix notation for this. So the vector of derivatives on the left side, I can literally just think of that as taking the derivative of the vector x, right? And then we see that this is a matrix here with all of these aij's in it. Of course, I will just call that capital A now. And notice that A is an n by n matrix. That's an important observation as well. And it is being multiplied by this column of x's. So A times x, and then to that we are adding this column vector of the b's right here. So here you see a even more compressed way of writing this linear system. This is all just about notation, okay? It's all just about notation. And I should point out that just as a quick definition, I'm going to try to squeeze it down here. I think it'll fit. A little definition here on the bottom of my board, which is that if the b vector is 0, if there's really no terms added on the end of every single equation here, if all of those b's are just 0, then this system is called, you guessed it, homogeneous. The same word that we seem to use way too often for way too many things. So then we call the system homogeneous. That's right. That would be a homogeneous system of differential equations, a homogeneous linear system of differential equations. That's if the b's are all 0. As you might expect, things are a little bit easier if the b vector is 0. In other words, if we have a homogeneous linear system of differential equations. And so we're going to start our discussion of linear systems of differential equations with homogeneous systems. We're going to start with homogeneous systems first, and then at the very end of this chapter, we'll spend just 45 minutes, maybe one short lecture talking about how to modify things for a non-homogeneous system. Okay, but for right now, we're going to focus on linear homogeneous systems of differential equations. And so here I've written down what that would look like. There's no b vector in this case because b is equal to 0 for a homogeneous linear system. And so it is simply going to look like x prime equals ax. And remember that A will always be an n by n matrix. It will be a square size. And for most of the pencil and paper problems that you would do on this topic, the n needs to be pretty small. Let's say either 2 or 3 generally. It's unusual to ask people to do calculations by hand with this material if n was bigger than 3. So one of the nice things about having the linear system be homogeneous is that we can take greater advantage of the linear algebra that has come before this. And I would like to state a theorem now that sort of shows you right away where the linear algebra can be useful. So this is a theorem that is worth writing down for sure. And what it says is that if we look at the set S, I'm going to call it S. If we look at the set S of solutions to x prime equals a times x, again, this is the homogeneous linear system, so the b vector is not here. If we look at the solutions to a system like this, which of course we're going to learn how to find those solutions soon, but if we want to look at that set of solutions, it forms an n-dimensional vector space. It forms an n-dimensional vector space. The solutions, they form an n-dimensional vector space. And that's where we then can take great advantage of the linear algebra that we've learned. We can find a basis worth of solutions, which would be n solutions. Again, n will usually be 2 or 3 if we're doing calculations by hand. Now, guys, this theorem would not work for the non-homogeneous system. Why not? Well, it wouldn't even pass the zero vector check. If I try to put in 0 for x, x is my solution, right? That's what I'm solving for. It's my unknown vector function. If we tried to put in the 0 vector for x, of course, the derivative of 0 is just 0. This equation would not work because we would have 0 on the left and we would have b on the right. And they would not be lined up. And so the 0 vector check would have failed for a non-homogeneous linear system. As soon as the 0 vector check fails, suddenly we don't have a vector space, which means we can't talk about a basis or a dimension or anything else really that has to do with linear algebra. So that's one of the main reasons why we really want to focus on these homogeneous linear systems, is because of this theorem right here. Let me just show you that this set S really will be closed under addition and scalar multiplication. We don't even need to really stop and check the 0 vector here. If I put in 0 for both x and x prime, I can see that this is going to be true. It's going to pass that 0 vector check. But what about the closure under addition and scalar multiplication? Let's just remind ourselves, and this is good practice with subspaces anyway, to remind ourselves how we could write something like this up. So I would need to take two solutions. Let's just say they're both vector functions. Let's say x1 and x2. Those are both elements of S. Let's just say that, okay? And the goal would be to add them together and make sure that when we add these two solutions together, that the result is still in S, okay? Well, again, what does it mean to have these vectors being in S? It means that they are solutions to our homogeneous linear system. If I plug them in for the unknown on the left and on the right, it's supposed to work, right? We're supposed to have a solution there. So let's just add that to the notes here. This just means that the derivative of x1 is a times x1, and the derivative of x2 is a times x2. That's what it would mean. Okay, but of course, we really are more interested in x1 plus x2. So I'm going to take a look at that. I'm going to add x1 and x2 together. We're doing this on a very abstract level here, right? We don't have specific functions in mind right now. We're just trying to understand this in a pretty generic sense. I would like to know, if I take the derivative of that, do I just get a times that? Because that's what S would consist of. Solutions whose derivative was equal to a times itself, right? That's the boxed equation that we're studying right here. Well, the first thing I would do with this is I would remember that derivatives respect addition, right? I could certainly add the derivative of x1 to the derivative of x2 as two separate calculations. And then each of those derivatives can be replaced using what we were told. We were told that x1 prime is ax1 and x2 prime is ax2. All right, so we can certainly do that. I need just a little bit more room here, I think. Give myself that room. Right, so take a look at what we have here, guys. This is ax1 plus ax2. I'm sure you all are thinking ahead that what we might think about doing there is factoring the matrix out into the front. And that's exactly what I want to do. So we end up getting the derivative. So let's take a look at the big picture again here, guys. The derivative of x1 plus x2 is equal to a times x1 plus x2. And so that certainly means, therefore, thus, x1 plus x2 is an element of S. No doubt about it. No doubt about it. Okay, so we get closure under addition. Now, similarly, we can prove closure under scalar multiplication. So I'll just go ahead and talk about that for a moment here. Closure under scalar multiplication. This is the one where we have to grab a scalar. I usually like to call it k. So we take a real number k, and then we need to grab one vector from S. I'm just going to use the x1 as above. So let x1 be as above. And I would like to show that if I take k times x1, that it still belongs to S. And to check that, we have to take its derivative and make sure that it turns into a times the vector k times x, right? So or in this case, k times x1. As we all know, derivatives respect scalar multiplication, so I certainly can pull the k out in front of that derivative. Once I do that, I can replace the x1 prime with a times x1, like so. And k is just a number, and so although we normally have to be a little careful about the order and switching orders of things when there's matrices around, in this case, k is just a number, and numbers can be floated in or out as much as we like. I'm going to put that k right in front of x1 there on the inside, because this is what I really wanted to get, isn't it? The derivative of kx1 is equal to a times kx1. All right, so that concludes that k times x1 is an element of S. Remember, guys, when you're showing subspaces, don't forget the punchline, right? Don't forget these punchlines that we have here. If we don't write that down at the end, we sort of have missed the big prize, the big thing that we were trying to argue. So we definitely want to make sure that we put that in there. Okay, fantastic. Well, let's just pause and soak this up for just a second. All right, so based on this theorem, we now know that if we have a homogeneous linear system of differential equations, that its solutions will form an n-dimensional vector space. And as soon as we have that fact established, well, now we're really going to want to go to town on trying to find a basis for that vector space, right? That would be n basis vectors, right? This is n-dimensional. We would need n basis vectors. And first and foremost, those basis vectors will need to be Li, linearly independent. And so this gives rise to a question, because we've never really worked with a vector space that consists of these vector functions before. So how do we test for linear independence in this context? That's really the natural next question where we need to go with this. So I'm going to phrase that over here for the notes as a question. And then it turns out it has a very innocuous answer. It's not going to be anything too crazy. I think you guys will be just fine with this. But let's just phrase it as a question first of all, which is how can we tell if n vector functions, again, normally n will be 2 or 3 for hand calculations. How can we tell if n vector functions, let's say x1 of t, and then maybe x2 of t, and then we're going to go dot, 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 right, up to xn of t. Let's say we have all of those vector functions. How can we tell if those vector functions are, in fact, Li? Right, this is a reasonable question to ask. Okay. Well, when we were dealing with scalar functions in studying nth order linear differential equations in the previous material, we introduced something called a Wronskian, and there was a matrix associated with writing that down. It turns out that there is also something similar here as well. The answer here is that we are also going to develop what I'm going to call a Wronskian. So the Wronskian in this case is not going to be the same Wronskian that we have seen before. Okay, so it's the spirit of this result is exactly the same as before. Namely, as long as the Wronskian is not 0, then my solutions will be Li. That is going to be the same. But the way that we construct this Wronskian matrix is a little bit different. So let me give you the definition here. It's actually easier, I think, in this context. It's actually easier. So the way that this Wronskian works, I'll call it W again. This time, instead of n scalar functions, we are going to be plugging in n vector functions. So with the previous Wronskian, we just had scalar functions that we put on the top of the matrix. Do you remember this? And then we started taking derivatives down the matrix until it was a square size. So we had derivatives that we had to take along the way when we were constructing the Wronskian for a set of scalar functions. But this is a different universe now. Each one of these x's, x1, x2, x3, and so on, each one of them already fills up an entire column. It's a vector after all. It has slots. And I can think of those slots as being vertically situated into this column configuration of this matrix. We are going to calculate a determinant again. But this time, guys, we don't actually have to take any derivatives. We just have to lay the x's sort of as is into the columns of this matrix. And that will make it into an n by n matrix right away. Okay, so we don't need to take any derivatives here. We just have to take the vectors themselves and lay them into the columns. And then if we are willing to accept that definition of the Wronskian, then we're going to get a theorem that should look very familiar to you, right? Because the result now is going to be basically the same. Namely, what it's going to say is the same result as we had for the earlier Wronskian, which is that if there is a value of t, now the previous Wronskian, it was a value of x. But here, the unknown function is generally being written as t. If there is a value of t, let's say t naught, right, such that w of x1, x2, and dot, 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 up to xn of t naught is not 0. If we can make even one value of t naught that makes that Wronskian not 0, then my functions x1 and x2, these are vector functions. Be sure to draw vector arrows on top of each one of those x's so it's not confusing. But each one of those x's has a vector on top of it, and as a set, that would be an Li set in that case. Okay. So just like the Wronskian that we had for scalar functions, this matrix that we are working with is not a matrix of numbers anymore. It is a matrix of functions, and every single column is a vector function of t. So you're going to have t's everywhere throughout this matrix, right? That's the idea. And so you're calculating that determinant kind of as a function of t. And if you can plug in a number for t, I'm going to call it t naught in the theorem here, that makes the Wronskian not zero, even one number, if there's even one number that accomplishes that, then your functions are Li. This is the Wronskian test, and it's proved very similar to the proof of the Wronskian test for scalar functions, which I have done in the past. You have seen that before. It's already in your notes, I hope. And so I'm not going to prove this particular Wronskian test, but rather I just like to show you an example or two of it, and then we're going to be in really good shape. All right, so let me erase my board. Okay, so I would like to practice this Wronskian test, this theorem, the W test, as I like to call it, on an example. Okay, so here's an example. I'm going to give you three vector functions, each of which has three slots. So the question is the set consisting of, now I'm going to make three column vectors, right? So the first one might be t plus 1, t minus 1, and 2t. All right, and then my second vector might be e to the t, e to the 2t, e to the 3t. Right, and then finally my third one might be 1 sine of t and cosine of t. Okay, and the question is that set of vector functions Li or LD, right? It's one or the other for sure. Okay, so this is the question that I'd like to have us think about. So keep in mind that each one of these columns is one of my vector functions. So I have an x1 here, this one might be the x2, and here's x3. It actually doesn't matter what order you choose to list these vectors in. It's obviously not going to fundamentally change anything about the linear algebra. So the issue of linear independence shouldn't really depend on what order I've listed them in. But in order to do a problem like this, we are going to use the Wronskian test, right? I'm going to use the Wronskian test, which I will just call the W test here. So W of x1, x2, and x3. Well, this would just be the determinant of a matrix that I get. And remember how the Wronskian is defined over here. All we need to do is lay those x's directly into the columns of a matrix. It almost seems too easy, right? We don't have to take any derivatives in this case. We just literally write down the vectors exactly as they were given to us. So the first column is exactly the first vector, okay? The second column, that's e to the t, e to the 2t, e to the 3t. We just lay it into the second column of the Wronskian matrix. And then the third column is 1 sine of t and cosine of t. Okay. Now, as I said, this is a matrix not of numbers, but of functions. And it is 3 by 3. If we wanted to right now, we could start working on the determinant by doing, for example, the arrow method. But you can see it's going to kind of be messy because, you've got all these functions of t in here. And so you're going to write out a whole bunch of terms and see whether you can plug something in for t to make the expression be not zero. That's how the Wronskian test works. Can I plug in a number for t that makes this Wronskian not zero? What I would recommend that we do, instead of sort of generically calculating this determinant, I would suggest that we try a couple of values of t up front that are easy to plug in and just see where we're at with this thing. Because, it would be nice if we could just find a value of t kind of just willy-nilly right off the top of our head that would work. So for example, one of the easiest values of t that you could ever think about using would be 0, right? And so what we can do is before using the arrow method, we can actually go ahead and just plug in 0 everywhere throughout this matrix, right? So obviously 0 gets plugged in and we turn this into a bunch of numbers now. So the first row would be 1, 1, 1. The second row would be -1, 1, and 0. And the third row would be 0, 1, and 1, right? I'm just evaluating every single slot by plugging in t equals 1. And this is what you would end up getting. And so you can calculate this determinant using the arrow method now very easily. And guess what, guys? This determinant, actually, I'm not going to show you the arrow method details, but I can tell you that it's not 0. Just happens when we got lucky right away. The first value of t that we tried, when we substituted it in to all of the parts of our matrix, we ended up getting a non-zero Wronskian. And what our theorem says here is that as long as there is even one value of t naught that makes the Wronskian not zero, then we win, right? Then the vectors are Li, and we're happy with that. Okay, so in this case, we already can say yes here, right? This is yes. And I'll just say by the W test, by the Wronskian test. Now, the question does come up. It's a reasonable thing to ask at this point. What if we had gotten zero here? You know, if we tried a value of t and we got zero the first time, right? That doesn't necessarily mean that these vectors are going to be LD. It might just mean that we got unlucky. We picked a value of t that did not work. And so what I would recommend is that if you've tried one value of t and you get zero, maybe try a second value of t, just in case you might have gotten unlucky. And if you try a second value of t and now the Wronskian of that value of t is not zero, then you're still good. You still have a linearly independent set. It just took you a couple of tries to get there. But if you got zero again for a second time, then you start to get suspicious. I wonder if these vectors are going to be Li or not, right? You could maybe try a third value, right? And maybe even a fourth value. But if you try enough values of t and you keep getting zero on every single one of those values, then you really have to start to ask yourself, I don't know. I wonder if these vectors are actually LD. And if they're LD, no matter how many values of t you tried, you will never successfully get a non-zero Wronskian, right? You would get zero every single time. So at some point, it becomes fruitless to keep just trying values of t. At that point, you really should think about whether this determinant is always just going to be identically zero. Let me show you an example of some vectors that are actually LD, so you can kind of see what I'm talking about, right? So here's a second example of kind of the same idea as what we were just talking about. So is the set, I'm going to make this one a smaller example, guys. Let's say that we took, I don't know, 5t squared, and maybe we also take a t plus 1. Okay, and then let's take a second vector, which is, let's say it's 50t squared and 10t plus 10. Now, if you just look at those vectors, you can see how I came up with this, right? Basically, I picked two vectors that are literally just scalar multiples of each other, right? The second vector is really just 10 times the first one. So we already kind of know that these vectors are LD, right? When one of them is a scalar multiple of the other one, they're going to be LD. Let's just pretend for a minute that we didn't see that, right? And we're asking whether these vectors are Li. Sorry, I can get my question here. Is that set of vectors Li? So if we didn't notice that these were scalar multiples of each other, of course, we might be inclined to just look at this Wronskian test. So the W here, in this case, these vectors would be just x1 and x2. We only have two of them. And we could do the Wronskian of x1 and x2, right? And it would just be the determinant of the matrix when we put these vectors into the column. So the first column would just look like that. And then the second column would be just like this. Okay, so there's your all-important determinant that you would need to think about working with, right? That's the Wronskian determinant. And, you know, if you follow my advice from earlier, the advice would be, well, just try some values of t, right? So you could, for example, you could evaluate this at, you know, I'd probably start off again with a value of 0 here. Right? And again, if I plugged in 0 everywhere I have a t, well, then I'm going to get 0 and 0 and 1 and 10, right? And I can see that that determinant is equal to 0. Okay, so that's not Not good, right? That's not what we want. Okay, so then maybe you could try a different value of t, right? I'm going to go ahead and erase this if you don't mind. Feel free to pause the video if you're still taking some notes on it, but I'm going to just erase this because I don't need to make a big fanfare of this whole thing. Let's suppose we tried a different value of t. Let's say we tried to plug in 1 instead. Well, so then what would we get? In this case, then, if we plugged in 1, we would get 5 and 50 and 2 and 20. And we could calculate that determinant. And what you're going to see here is that again, you get 0, right? Using the little 2x2 determinant formula. Again, we're not happy with the result. We got 0 again, right? And if we keep trying other values of t, we will keep getting 0 every single time, right? It becomes more and more hopeless each time. It's like, oh, we keep getting 0. I wonder if maybe there's not going to be a value of t. Well, once you sort of become suspicious that there's no value of t that's going to work at all, then the way to really have some peace of mind about this and totally convince yourself is to actually take the determinant as is with the t's in there. Leave them in there, and that way you're getting the general expression for this determinant that would be for any value of t that you could ever think of. So if I use my 2x2 determinant formula just on the general matrix with the t's still in there, right? So AD minus BC is going to look something like this, right? This would be the actual generic expression for the determinant. And if you actually work this out, so you can factor a 10 out from here and put it with the 5, and that makes 50. And then everything else is the same. And so this is actually equal to 0, regardless of what t was, right? This is always going to be equal to 0, no matter what your t value is. And that really settles the matter. That really settles the matter. The answer here is no, these vectors are not Li. Again, we already kind of knew that. The second vector was literally just 10 times the first vector. But now we've sort of seen how it would work with the Wronskian test if we just decided to play the game, right? If we just decided to go ahead and do the Wronskian procedure, that would be the conclusion that we would draw. Okay, so just one last little bit to this talk, guys. If we've got that Wronskian test behind us, I want to just give you a quick definition and then a quick little hint about how we are actually going to come up with these solutions for ourselves, okay? So this is kind of the big deal. So let me write down a quick definition, just so we have this in the record. This is pretty standard terminology, nothing too crazy. But if we have x1 of t as a set, the set of x1 of t, x2 of t, and dot, 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 up to xn of t, if that is Li, so if we have managed to convince ourselves that it is Li, and each one of those, let's say xi prime of t, is equal to a times xi of t for all I. Okay, so if that set is Li, and this is just saying that it satisfies our homogeneous linear system, right? That's what that is. If we know that, then we call the matrix, which I'm going to create here, this is a definition. It's generally going to be written as capital X of t. This is also going to be an n by n matrix, just like A itself was. But what we have here, so let's be very clear about that. A is also n by n. Then this matrix, which is defined as essentially what the Wronskian matrix was. The individual vector functions x1 through xn are laid out into the columns of this matrix, right? This is what is called a fundamental matrix. This is called a fundamental matrix. So I just want you to know that word for the linear system, x prime equals a times x. So a fundamental matrix is just a matrix whose columns consist of n linearly independent solutions to our linear system of differential equations. It's n linearly independent solutions. Remember, that's a basis worth, right? The solutions form an n-dimensional vector space. If we have n linearly independent solutions, this is wonderful. This means we have a basis worth of solutions to our homogeneous linear system, which basically means that, we're in great shape. Every solution is just a linear combination of those basis vectors, right? That is so nice to have, right? So this is, by the way, this is an invertible matrix as well. I should mention that's another good thing about it. Why is it invertible? Feel free to stop the video if you want to answer that question before I tell you the answer. You can pause and think about why this matrix would have to be invertible. And it goes back to the invertible matrix theorem, which has a whole big long list of things. And one of the things in the list is that an invertible matrix would be one where the columns are Li. And that's exactly what we've said here. These columns, x1 through xn, are Li. So of course, this is an invertible matrix. We're actually going to need to use the inverse of this matrix eventually. So we haven't quite gotten to that yet, but soon enough, we're going to be looking at the inverse of this fundamental matrix, capital X. Okay, so I want to finish this video now with one last question and answer for you. Okay, one last question and answer for you, and this is a natural one to be asking at this point. We've just said over here that if we can find n linearly independent solutions to our linear system, that they will form a fundamental matrix for us, and they will be a basis for all of the solutions to that linear system. That's a big deal. But the question that we would then want to answer is, how in the world do we actually come up with n linearly independent solutions to our homogeneous linear system? This is where the rubber hits the road. This is what we really want to know. How do we find these solutions? And the answer is an absolute thing of beauty. I absolutely love it. This is one of the reasons why this is like my favorite material to teach, is because this is going to take us back one more time to a very important part of our linear algebra training, okay? Because this is a square matrix A. And because it is a square matrix A, that matrix, as we learned earlier in linear algebra, it will have eigenvalues and eigenvectors, right? It will have eigenvalues and eigenvectors. So the answer here is, I'm going to suppose that lambda and v is an eigenpair for A. I mean, who would have thought? Who would have thought that the eigenvalues and eigenvectors of A would have anything to do with what we're talking about in this systems of differential equations conversation? Who would have thought? It actually does. Because what I'm going to do, guys, is I'm going to consider a function. I'm going to call it x of t. And here's what it is, guys. It is going to be equal to e to the lambda t times v. I know that that looks like it's coming out of thin air. Where did he get this from? But it's actually quite amazing that if you take your eigenvalues and eigenvectors in their pairs and form these vector functions, right? These are basically the eigenvectors with a scalar in front of it. The scalar is where the function of t really has its presence. It's out in the scalar in front. The vector will have specific, numbers inside of it. But there's a t right there, and that makes this a vector function of t. And here's what I want to do, guys. I would like to take the derivative of this. Watch this, okay? So I'm going to put this in a different color just to really make a big deal about it. If we take the derivative of that thing, okay, how do we take the derivative here? The v is really just a constant vector. And so I'm really just going to be taking the derivative, how when you take constants. They just come along for the ride when you take derivatives. So I'm really just differentiating e to the lambda t, and we know how to do that. The lambda just comes down in front, and we get lambda times e to the lambda t. But now I want to point out that we can just as well go ahead and move that lambda over there with the v. I'm going to just rearrange the scalar lambda so that it's in front of the v right here. And my reason for doing that is that one of the most important things that we know is, well, in fact, what I like to call the most important equation in the theory of eigenvalues and eigenvectors is that lambda v is actually the same thing as AV. You guys remember that? If we have an eigenpair, right? The most important thing about eigenvalue, eigenvector pairs is this right here. AV is equal to lambda v. So I'm going to take lambda v and change it to AV. And now, again, because e to the lambda t is just a scalar, it's not a matrix, it's literally just a number for every value of t. I can actually pull the matrix out in front and write this as A times e to the lambda t times v. But guys, what is that? That's just A times x of t. That's just A times x of t. In other words, what have I just shown here in blue? X prime equals AX. Isn't that our homogeneous linear system of differential equations? We've found a solution to it by using the eigenvalues and eigenvectors of all things. Right? So by using the eigenpairs of the matrix A, we can generate solutions to our linear homogeneous system of differential equations by just constructing these things right here, e to the lambda t times v, right? And so if we have a lot of eigenvalues and eigenvectors, we can make a lot of solutions. On the other hand, if we have a defective matrix, that could be an issue. If the matrix A is defective, we might have trouble coming up with as many linearly independent solutions as we need. So this is going to be the next thing we're going to talk about, the difference between a non-defective and a defective linear system of differential equations. But at least for now, I think we should just bask in the wonder of the fact that the eigenvalue eigenvector theory that seemed like it was purely about linear algebra is now surfacing in the middle of a conversation about solving systems of differential equations. It just doesn't get any better than that, and it really testifies that it makes sense to put these two subjects together in the same course. So I hope that you've enjoyed the video. If you have questions about it, be sure to jot them down and send them my way. I love talking about this stuff, and I'll do whatever I can to help you understand it even better. Thanks for your time on the video today, guys, and I'll see you guys all again very soon. Bye for now.